So now we're going to look at numeric summary measures. Now these are all the hardcore statistics things that you've probably seen before, and specifically we're going to focus on a salary variable as we talk about this, because that's going to go along with our example, which is going to be baseball salaries that we'll do at the end of this section. And so the kind of things that we're going to quickly go over is measures of central tendency, and that's basically the 3 M's: mean, median, mode. Max, min, percentiles, quartiles. How do we measure variability? So empirical rules for interpreting standard deviation, measures of shape, and numerical summary measures. And so the first one that we want to look at is those measures of central tendency. Now, the first thing that we have is mean. Through this section, you're going to see equations, and it's okay. I'm not expecting you to be able to write out these equations or remember what they are. I do have them in there so we can see what Excel's doing for us. As you're going to see in the Excel example, this stuff, Excel calculates out for us pretty easily. But I do have the equations in here because I'm a math guy. I like looking at them, and I think it's important to kind of know what is going on behind the curtain. So the mean is just the average of all the values. We add them all up, we divide them by the number of values. That's it. That's all it is. And so a sample mean will be denoted by X with that little bar over it, and we call it X bar. Once again, now this is where we're going to get into, there's slight differences between the sample and the population. We're almost always going to be dealing in the sample, but it's important to know the population stuff because we are later in the class going to be trying to predict what's going on in the population. So it's a sample mean if it's dealing with the sample. It's a population mean if it is dealing in the population. Now the important thing to remember is if we're dealing in a population is we're going to be using this Greek letter mu to denote what the population mean is. So our mean, how do we put it together? It is simply we just take all of the values together. That's what X is. Just X by itself is a value. I is the indexing, so we're talking about, X is going to run from I equals 1 to N, N being the number of points in our data set, and so we just take that, multiply that, or add that all together, divide it by the mean, divide it by the number of instances we have, which will give us the mean. So in Excel, we can easily calculate the mean. We just use a function called average. Average, we select the data cells, we're good. The second of our 3 M's is the median, and that's the middle observation. So you sort the data from the smallest value to the largest value, you pick the one in the exact middle. So it's basically the median has just as many values to the left of it as it does to the right of it. And so in Excel, we do have a median function. And knowing where the median and the mean are and how they relate to each other can tell us stuff about the population distribution. And so the last one we have is the mode, and that's the value that pops up the most. And it depends if it's going to be interesting or not. If it's a continuous variable, which means that you have those infinite variables, the mode's not really going to tell you anything. The mode comes into play like, say you have 2 dice and you throw the dice and you're tracking the number of times everything comes up. The mode of that curve would be 7 because it has the most combinations. It will show up the most amount. Mode is not something that we're really going to be dealing with a lot in this class. But if we did want to calculate the mode, Excel does have a function that is the mode. So something else that's interesting to look at is what are called percentile and quartiles. And this is something that we'll be using quite a bit when we deal with our probability distributions. So percentile is the value that the percentage of all the values are less than it. So if you have kids, or if you remember going to school and you took those little achievement tests or whatever they're called now, and you get to the point and it's like, it says you're in the 80th percentile in math. Well, what does that mean? That means that they look at all the people's scores and 80% of the people are lower than what score that you've got. That would be the 80th percentile. If you were in the 95th percentile, it means that you are better than 95% of all the values. If you were in the 15th percentile, that means that you are only better than 15% of all the values. So that's what the percentage is. The quartile is a specialized percentile where the first quartile would be the 25th percentile, the second quartile would be the 50th percentile, and the third quartile would be the 75th percentile. And so by definition, that second quartile should be the same as your mean. So it's just a way of parsing data and taking a look at it. We do have a minimum and maximum. That's just the smallest and the largest value in our data set. And we can calculate those with the min and the max function. And percentiles and quartiles, there is a percentile and quartile function in Excel, which in the example that we will look at, I go through all of those and how to use those. So definitionally, range. What is the range? The range is the minimum value to the maximum value. That's the range over which the data occurs. Now we do have something that we look at quite a bit in statistical analysis called the IQR, or the interquartile range. And so it's the middle 50% of the data. We take the third quartile, we subtract the first quartile, it gives us that middle 50%. Why do we even look at that? Why do we care? Because that data is less sensitive to extreme values. If you have outliers that can throw the data off, the IQR is a little bit more stable because you're looking at the middle 50%. We can measure variability also by calculating the variance. So what do we do with, how do we calculate out the variance? We take our observation, we subtract from it the mean. So you'd find the average of the sample, then you would go through every single data point, subtract the mean from it, and then you would square it. You square it, gets rid of those nasty negative numbers, and so everything will be in the same direction. And so once you do that, this gives you the variance of the population. Now, if I want to look at this in equation form, the sample variance would be S squared. The population variance would be sigma squared. Once again, this is going to be important, realizing there's a distinction between these two once we start getting on to things like probability distributions. Sample and the mean are two different things, so we have to realize that we have two different variables showing that. And you can see the difference between the two. Sample mean uses n-1 for the number of samples, and the population just uses n. So if the observations are all close to the mean, that tells us that we don't have a lot of variance. If there's a couple of them that are far away, though, that squared function will end up getting kind of accentuated. It makes it bigger, causes a bigger variance. So in Excel, we'll use var.s for sample variance, and we will use var.p for a population variance. Now, there is a problem with variance, is that it's going to give us things in squared units because we end up squaring it. And those units don't really mean much because dollar squared, there is no such thing as dollar squared. So a more natural measure that you will see all the time is STDev, or standard deviation, which is just the square root of the variance. So the variance gets rid of all those nasty negative numbers, and then the STDev gets rid of that squared number. And once again, we have a sample standard deviation, we have a population standard deviation, so S and sigma respectively, and we can use stdev.s to find the standard deviation of the sample. stdev.p will give us the standard deviation of the population. So as we look at standard deviations, we have some empirical rules that we can take a look at. And so empirical rules mean that it's just commonly observed. It's what we see. It's not theoretically proven. So anytime anybody's talking about empirical data, it just means observed. We take a look at it. And so typically what you end up seeing is 68% of your data is going to fall within one standard deviation of the mean. 95% of your observations will fall within two standard deviations, and 99.7% will fall within three standard deviations. And so this is where, if you've dealt with it before, and we'll talk about it later in this course, 6 sigma comes into play, because a sigma is a standard deviation The whole idea of Six Sigma is your 3 standard deviations away from the mean on either side, that's where the 6 comes from. If you have no idea what I'm talking about with Six Sigma, we'll talk about that later in the class because it is a big thing in manufacturing. Certified manufacturing accountants will run into it, but it's a little beyond what we're doing right now. And so empirical rules should be looked at with a little bit of caution, especially if the data is skewed. What do you mean by data skewed? We'll talk about that actually after this next example, but it's just there, it's empirical, it's rule of thumb, it's good to know. So how can we interpret standard deviation? This is something that we are going to look at quite a bit, and we're going to get mad about it. We're going to use the mean absolute deviation. And so this is the averages of all the absolute deviations. So I take the actual value that I've got, subtract the mean, add those all up, divide by the number of observations they are, and this gives us the MAD, the mean absolute deviation. We can use the average dev function to calculate MAD. Typically I don't do that. Typically we'll do the average and then we'll divide it all out, but we'll see that all in the class. And so this gives us another empirical rule. For many variables, the standard deviation is approximately 25% larger than their mean absolute deviation. Once again, empirical. This is not an absolute measure. It's just a rule of thumb. You can look at it kind of thing. So one last thing that we want to talk about before we look at the example is measure of shape. So we'll talk about skewness in our graphs during this class, and that occurs when we have no symmetry. So you can be skewed to the right, which is positively skewed, because you have some large values. And so what that does is that kind of drags your distribution to the right. And so it is skewed to the right because you have the long tail on the right, and I'll show the pictures here in a second. Or you can be skewed to the left because of some really small values. So if you're measuring temperature lows in Antarctica, it gets cold there. I've had a friend that went there she collected meteorites. It's cold. So it kind of skews the data off to the left, and so you have a long tail off to the left. We can measure skewness in Excel using the skew function. So this is a couple of distributions showing how a distribution is put together. So this is just all the data points that we've put. We've plotted a curve on them. Right here in the middle, there's our measures of central tendency, the mean, median, and mode, those 3 things that we have. And so what happens? Well, here's the positive skew. This is the tail. You can see it's longer than the other ones. That's why it's a positive skew, or it's a right skewed data because it is from the long tail. The mean is greater than the median because we're pulling things over this way. Negative skew is the other way. The mean is slower than the median. So once again, median. The number of data points on this side are the exact same as the number of data points on the other side. So this is negatively skewed. I always got screwed up with this because I'd always look at this and go, oh, this is right skewed because the mode is to the right. But no, it's talking about the tail, not where the mode is. So in statistics, the mode, the skewness in here is used quite a bit. And so this is also how data can be positively and negatively skewed. And it's all about that tail. Now I do want to talk a little bit more about shape, and we're going to do that in the next video before we do the example. If you have any questions, please let me know. Otherwise, I'll see you in the next video.